So now that we've taken a look at the squeeze theorem, it's about time we take a look at the intermediate value theorem, which we'll abbreviate as IVT, because who could bother writing out intermediate value theorem all the time? And this is actually the second and kind of final, I suppose you could say, crucial theorem that we're going to learn for limits in Calculus 1. Of course, there are many different theorems that we'll learn as time progresses. However, as of right now, all we care about in Calculus 1 is the squeeze theorem and the intermediate value theorem. Now, this one is a little bit more convoluted than the squeeze theorem, and you may not find as many practical applications of it. However, we'll do a couple of examples to illustrate how we can, or different exam questions actually, that you may find using the intermediate value theorem. So, what this theorem states is that if we have a function f of x, which is continuous over this interval, this closed interval from a to b, such that f of a is not equal to f of b, and a lot of times you'll actually see that f of a is strictly less than f of b, which we could mention if you'd like, then there exists, that's what this backwards e means, it means that there exists some k value that's contained within the open interval from f of a to f of b, and some c value which is contained within the open interval from a to b, such that f of c equals k. I don't know why that parenthesis is not there. So such that f of c equals k. And so this may seem a bit odd, and you may be thinking, wow, this doesn't really seem useful at all. However, when you do get into the proof of it in real analysis, and you may find that it is quite useful for not only learning its proof, however, proving other different theorems using the intermediate value theorem. But as of right now, these are the types of questions that you may find on your AP exam, which require you to use the intermediate value theorem. So we have this very nice quadratic function over here that's defined for this closed interval from -3 to 2 for x is a member of. That's kind of what this little e or epsilon looking thing means. And the hypothesis or the conjecture that we're trying to prove or disprove is that this function has zeros within our interval. And so what we can do is we can first of all, look at the definition of a zero. A zero is some k or some x value, which we'll refer to as c, such that f of c equals 0. So we have our c value over here. Here we have our k value. We said k equals 0 if you want to go back and look at this thing over here. And so what is very useful to do is actually determine the endpoints, I suppose you could say, or the boundary points. So we have f of -3, which is going to be 9 minus 21 plus 10, which is just going to be -2, if I'm not mistaken. And then we have f of 2, which is going to be 4 plus 14 plus 10, which is going to be equal to 28. So we have these two endpoints over here, the boundary points. We have -2 and 28. This -2 may be viewed as like f of a, and this 28 is kind of like our f of b, if you will. And so now that we have our lower bound and our upper bound, we can actually take a look at our k value. Our k value is k equals 0. And is it contained within the open interval from f of a to f of b? And let's actually go ahead and verify that. So is 0 strictly greater than -2? And in fact it is. And is it strictly less than 28? And we can also verify that. So we know that at some point within this interval, there does exist a c value that is contained within the interval such that our function is equal to 0. And so there does exist such a c value. And what we can also do is actually verify what that c value is. So, we can factor this polynomial, and we'll find quite easily that the zeros of this function are -5 and -2. It's a very easy polynomial to factor. And so we actually do have two zeros for this function, which makes sense since it's a quadratic function. But the 0 that we actually care about is the 0 that's contained within our interval from -3 to 2. And so although -5 is technically a 0, we don't really want to focus too much on it because it's not contained within the interval. So the 0 that we do care about is x equals -2, because -2 is contained within the closed interval from -3 to +2. And so then we can actually say that our c value is equal to -2. And we're able to verify that it exists. Like, we're guaranteed that this c value exists within this interval because of the fact that, we have the intermediate value theorem at our disposal. And another type of question that you may see, and this one I actually got from Khan Academy because it is a little bit difficult to come up with questions for the intermediate value theorem, but this type of question will actually illustrate how we can use the intermediate value theorem to analyze function behavior. And so we have an arbitrary function that's continuous over the interval from -2 to 1 over this closed interval, such that f of -2 equals 3 and f of 1 equals 6. So they gave us the boundary points, if you will, from 3 and 6. And so what we can do now is we can actually analyze different things about this function. So we can say, is there a by the intermediate value theorem, is there a c value such that f of c equals 0? So does the intermediate value theorem guarantee the fact that we will have a 0 within this interval? And so what we can do is we can look at these endpoints from 3 to 6, and so we can try to verify whether 0 is within this interval, and it's absolutely not within this interval. 0 is not contained within the open interval from 3 to 6. And so we can say that the intermediate value theorem doesn't guarantee the fact that there are zeros within this interval. And so that doesn't necessarily mean that there are no zeros in this interval, like maybe there are. However, the intermediate value theorem doesn't guarantee the fact that there are zeros here. But, and another example of that is, f of c equals -1, for example, or really any negative number. We can verify immediately that -1 and really any negative number is not going to be contained within this interval. And so with these two examples, we can say that, the intermediate value theorem does not guarantee that these two statements hold true. Guarantee. And so, although maybe the function is negative over this interval at some point, or maybe it does equal to 0 at some point, this statement can be guaranteed without actually being given the function. So with just the intermediate value theorem alone and just these two pieces of information, we can't actually guarantee that we're ever going to be negative or that we're ever going to be 0 within our interval. And although we may be 0 at some point, the intermediate value theorem doesn't really, give us a definite proof that we're going to be 0. However, for example, if we chose f of c to be equal to 4, then by the intermediate value theorem, so we know that 4 is contained within the interval from 3 to 6, so that does hold true. So the intermediate value theorem does guarantee that at some c value, regardless of what that c value is, we don't really know what this function is like or what the function's equation even is, but we do know that at some point within this interval, at some point, at some point within the interval from -2 to 1, there is a certain c value that will make our function equal to 4. Maybe there are multiple c values such that that holds true. However, regardless of what that c value is or how many there are, all that we care about is the fact that the intermediate value theorem does guarantee the statement. So this is guaranteed. Guaranteed. I don't think I'm spelling guaranteed right, but the point is we can use the intermediate value theorem to kind of at least get a general understanding of how the function behaves. Again, we're not guaranteed in these cases that it will be negative or that it will be 0, but we do have a general sense. We are certain that at some c value, we are going to be equal to 4. Our function is going to be equal to 4, and that's just a direct result of the intermediate value theorem.